really know where individual electrons are in this wire, but we do know the whole collection of them is drifting forward. There's something called drift velocity, which tells us how fast that drift is. This copper wire, it's only about 1.5 inches per hour. It could easily take an hour for the charge to get from the battery to the light bulb. But once the switch is flipped, the battery's electric field travels across the circuit at the speed of light. And all the charge in all the conductors moves at nearly the same time. The energy that makes a circuit work comes from the fields around them. A source of energy like a battery just replenishes what gets used. And all the electric current does is provide the mechanism we need to make the energy flow. Fields are everywhere and affected by all charges everywhere. The energy coming out of a power source doesn't have to be the same energy going into your devices. Conservation of energy just says they have to be the same amount. If you calculate the amount of energy flow across the surface of this wire, you will get exactly what you'd expect for the power lost to heat and light.
Simple circuit with a battery and a light bulb. The battery by itself has an electric field, but since no charges are moving, there is no magnetic field. When the battery is connected into the circuit, its electric field extends through the circuit at the speed of light. This electric field pushes electrons around so they accumulate on some of the surfaces of the conductors, making them negatively charged, and are depleted elsewhere, leaving their surfaces positively charged. These surface charges create a small electric field inside the wires, causing electrons to drift preferentially in one direction. Note that this drift velocity is extremely slow, around 1/10 of a millimeter per second. But this is current. The charge on the surfaces of the conductors also creates an electric field outside the wires, and the current inside the wires creates a magnetic field outside the wires. So now there is a combination of electric and magnetic fields in the space around this circuit. So according to Poynting's theory, energy should be flowing. Along the wires, again, you can use the right-hand rule to find the energy is flowing to the right. This is true for the fields along the top wire and the bottom wire. But at the filament, the Poynting vector is directed in toward the light bulb. So the light bulb is getting energy from the field. If you do the cross product, you find the energy is coming in from all around the bulb. It takes many paths from the battery to the bulb, but in all cases, the energy is transmitted by the electric and magnetic fields.
The answer to our giant circuit light bulb question. Well, after I close the switch, the light bulb will turn on almost instantaneously in roughly 1/c seconds. So the correct answer is D. I think a lot of people imagine that the electric field needs to travel from the battery all the way down the wire, which is a light second long, so it should take a second for the bulb to light up. But what we've learned in this video is it's not really what's happening in the wires that matters. It's what happens around the wires. And the electric and magnetic fields can propagate out through space to this light bulb, which is only 1 meter away, in a few nanoseconds. And so that is the limiting factor for the light bulb turning on. Now, the bulb won't receive the entire voltage of the battery immediately. It'll be some fraction, which depends on the impedance of these lines and the impedance of the bulb.